So now with the ABC thing, we can go to how do we solve a problem. This is the A, this is the B, this is the C. Now we want to minimize this thing, but we have W larger than 0, H larger than 0. Ignore this for a moment. This is called constraint optimization problem. You want to minimize this F. What's the lowest value here? 0. Can you get negative? No. What is this? You have a bunch of squares. So the smallest is 0. So that means the best you can get is 0. What is this? This means some x are illegal. What is the constraint here? We want the x to be, let's say, larger than 0. Any guy inside this cannot be a negative number. 1, 2, 3, 4. This is okay. 1, 0, 3, 4. This is okay. Negative 1, 0, 0, 0. This is not okay. So I want to solve this. People use k to denote time. You start with x0 because you need everybody inside Q. So you pick an x0 inside Q. Now you have x0. You want to get x1. You will do something called update. We are going to do something called gradient descent. Okay, I just write GD. Then after you get x1, you repeat the same thing here again. And then you repeat. You do many times until this is true. What does it mean? You have some stopping condition. Let's say your stopping condition is f value smaller than 10 to negative 12. If this is the case, finish. Your algorithm stop. So that means you keep making function value go down until you reach some value. Then you say, okay, I stop. What is this? You do a gradient descent of this. That means what? You have an x. What is this? This is a vector. So it's a bunch of thing. Now you have an f. F is a bunch of thing from your x. It gives you a number. So this is a vector to scalar function. Because you have a bunch of things, the gradient, okay, what is this? This basically means you have f. You do partial derivative with respect to the first guy, partial derivative with respect to the second guy, differentiation with respect to each of the component in your vector. And then this means what? Rate of change of your f at the first position, rate of change of your f with respect to the second variable, rate of change of f with respect to other stuff. So if your x is m-dimensional, then this should be an m-dimensional vector. And this is correct, why? Because this is a vector. This cannot be a number. Then you will have vector plus number, undefined. So this guy also needs to be a vector. So this is a vector, this is a vector. Then that means what? This tk is a number. This tk is called step size. Let's consider two dimensions. I call this thing my x0. I call this one my x1. So I will have x1 equal to what? x0 minus the gradient of my function according to my x0 with a step size I call it t0. It means partial derivative of my f with respect to x1 at my x0 value, partial derivative of x at my x0 value, which is just a vector of two numbers. This guy is a vector of two numbers. So vector of two numbers add a vector of two numbers scaled up by some number give me another vector of two numbers. Then a natural question is how do you find this? We will talk about it later, but here's a stupid trick. Since you don't know what is this number, you just try 0.1. Or if it's not working, then you make it 0.01. Or it's not working, then you make it 0.01. Basically, I think of this as a number, how much you move. So with this in mind, now you have what? You have an xk at time k minus step size at time k, which is just a number. You can think of it as a very small number. You have a vector, which is the direction of the function at that particular point. Why there's a subtract? Because you want to go down. So this is your new variable. This operation has nothing to do with respect to the Q. Everybody stay in Q. It's possible this thing will be outside Q. So what you do, make it go back to Q. This whole thing, the name is called projected gradient descent. Gradient is this thing, descent is this minus size, projected is this thing. It means I project back to Q. For our problem, we said that everybody needs to be larger than 0. So what is the projection? The projection is very simple. It just makes the negative number to 0. Suppose I have a number, okay, in a two-dimensional coordinate, x is 1, y is negative 1. So my point is here. Let me call it j. I have a point j. I'm saying everybody needs to be larger than 0. It means stay within this corner. Then what's projection? I need to find a guy in this region closest to this point, right? Because the distance between these 2 points, this is smallest. You won't say, okay, if I want to project this into this brown set, I should go here, right? You should find a guy that is closest to this. So what is this P thing? I have an input point J, right? Project onto Q. This is my Q. It means I find the argument of the minimizer of this. It means I need to find among all the y in the Q. That means everything in this brown region such that the distance between y and j is the smallest. Here is how you understand it. What is this? This actually is the equation of circle. y1 plus j1 square plus y2 minus j2 square, blah, blah, blah. What is this? This looks like equation of circle, right? This is radius r. So therefore, this is saying that I'm drawing a equidistant circle around my j. This is a radius r. This radius r is actually amount of the distance between the y and the j. But I want my y to be inside Q. So I need this circle to grow bigger until it touches the brown region. Let me draw like this. This guy is the point in Q, shortest distance away from my j. Then this will be what? The projection of my j onto the constraint. And interestingly, this is always a 90-degree projection. So this is also called orthogonal projection or Euclidean projection. Another example, suppose my Q looks like this. And suppose my j is here. Then where will it project? It will project onto here. But suppose my j is inside. What will be the projection? It will be itself. Why? Because this is saying that anything inside Q, shortest distance to J. If my J is already inside Q, which point is shortest distance to itself? Itself. So if my point is inside the Q, itself is the point inside this Q's shortest distance to itself, right? So therefore, do nothing. So that means this thing means if you are outside the set, project onto the closest point. If you are inside the set, do nothing. For our larger than 0 thing, we have this explicit form. I have a number, it's -1, which is exactly this example. The y coordinate is negative. What is the closest point in larger than 0 set, closest to negative number? 0. The y-axis have a value 0. But what about x-axis value? X-axis value is a positive number. Positive number is already larger than 0. So after the projection, it do nothing. So I keep my x-axis, but I change my y-axis value. So that means the projection gives me 1, 0. So this guy do not change. This guy change. And if I have a point here, x-axis is negative. So after the projection, it should x-axis become 0. But the y-axis is what? Positive. So y-axis do not change. What about if I have a point here? Both x and y are negative, so it should go here. Which makes sense because the circle that touches the set is exactly this point is the closest one, right? So how do you understand this? You want to minimize fx, x larger than 0. You do xk plus 1, new, that means new point or next point equal to what? Your current point minus gradient, okay, at your current point, multiply a step size, okay, minus means you go down, you want to go down. This point possibly is outside the Q, you project it back. If this point stay in the Q, then this means do nothing. Go back to our original problem. We have two variables, W and H. Consider this on W, fix H. And then what? Consider this on H, fix W, using the W obtained here. And then once I get the H, I go back to here. So you have a function f on W and H. I first use the W. This is a W step. You see, I write this, that means what? I fix the thing after this semicolon. This is a constant for me. And I update the W. So this gradient on W, my current W, this is step size on W. And then what is this thing? This means a negative thing go to 0, positive thing I keep it. This is the projection, okay? This is a W. After I update W, I use this W. Notice that is a k plus 1. I put it as a constant. Do the step on H. So this is, I update H. After I finish this step, I will go back. And now a k plus 1. So this H will go to here. So basically, this is what you do. This is what I do for one variable. This is what I do with two variables. That's it. Let me recap. You have a matrix like this. So this is what? 2, 5, 6. This is what? 2, 5, 6. This is what? Rice image. So this is rice. Okay. 86. So this is what? This have 86. This have 86. But this is 256. This is 256. Okay. I plot the x minus wh divided by x squared. So this is my rice image. So this is constant. It's an image. This you can think of this as a normalized everything between 0 and 1 and then time 100%. So it's like how much is the error with respect to my image. This blue point means I update one iteration on W. Red point means I update on H. Now I plot everything. You see, everything is going down. So in the very beginning, the error is about 9%. After I run 60 steps, it go down to 6%. Error from 9 to 6. So I have a rice image. And then what? Just randomly make some W1, H1. Does not look like rice. In step 15, it still will not look like rice, but if you keep going, after step 300, you cannot tell what's the difference between 300 and 500. These two basically are the same thing. Now I go back to the notation. So x minus WH, which is the same as the A minus BC. So what is the first step? You write everything as FB or equivalent as FW. And then second step, you write everything as FC or equivalently as FH. Then this, based on this expression here, and of course you need to do the projection thing, okay? I just write a big bracket P thing here. How do you choose this number? You try it with 0.01. Doesn't work, then you try 0.01. If it doesn't work, you just do this. This have a name called line search. You have a function. Now let's say I have a function that looks like this. You are now here. The gradient give you this direction. So minus t gradient, right? This is how much you move here. So this is my point here. So this amount is the t. Imagine if t is 9,000, you move to here. This is 9,000. Your step size is too big. And you make it small. Then you move to here. It's possible you don't decrease the function value because step size is too big. Then you make it smaller. Now you should see if I make my step size smaller, I will go down because this means my y value, the y-axis value, which is actually f, go down. What I need is just this guy go down. That's it. So this guy go down here. What's next? The gradient will set next time I should move this direction. Then that means here I should move this direction. How much I move is the t. If I move this amount, then I move from here to here. Right? And then the gradient is still pointing here. Because gradient always point down. So therefore, I just need to make sure this number is correct. If this number is too big, you can see I will explode, go to infinity. If my step size is infinity, I go to infinity. What's the limit of my step size? So this is the y value, right? Any step within this range, not this range. Because if I directly move to here, it means I don't move. I'm staying in the horizontal line. As long as I can make function variable down, that means I don't care how small, but as long as I'm going slightly down, I win. I just go down a little bit. So this gives me a range here. Actually, there's a theory telling you how you should design t, but not today. So basically, as long as your t is what? Larger than 0, because if t is 0, that means you don't move. And below an upper limit, I call it up, any value here, you will always like this, right? And you can see there are some values the best. For example, this one is the best. So we just know a range. So you just pick whatever value here. And if the value doesn't work, that means the function value go up. I just make it 10 times smaller or half smaller. Done. This is called line search, okay? And once you run this on W, fix the H, and then you go to H, fix the W, and repeat many times, because every time this function value will go down. Then of course, if you run long enough, it goes down. This is the backbone of all machine learning. And then, okay, here are the theory of how you choose a step size, but I'm not going to talk about it. This is the old method. I use some constant step size. That means my step size is always a fixed number. I never change. But if I do some optimal step size, you can see after 60 steps, my error for the old method moved from 9% to this. This is around 5.7% for 60 steps. It takes this method 12 steps to achieve the same decrease if I change the update rule. If you somehow know how to tune the step size, your algorithm run much faster than the stupid step size. 12, this is 60, so it's like 4 times to 5 times faster. Picture illustration. This is constant step size, this is optimal. This means iteration 1, both look the same. But in 5 iterate, this guy still looks rubbish. But this guy already start to have the rise shape. And then in 29 steps, this guy already have the contour. This guy is still a bunch of straight line and flat line. And after 500 steps, basically both look the same.